In recent years, a vast array of new and dramatically improved audio and video products has arrived on the consumer scene. Today's electronic technician must repair these products in which digital and linear integrated circuits abound. This video is prepared by the Consumer Electronics Group of the Electronic Industries Association. The EIA, strategically located in the nation's capital, is a full-service national trade association representing the entire spectrum of electronics companies. The Consumer Electronics Group is composed of more than 100 consumer electronics manufacturers and is responsible for communicating industry positions and developments to government agencies, financial institutions, the engineering establishment, consumer groups, the mass media, and the educational community. The Consumer Electronics Group also sponsors hands-on electronic seminars for technicians and educators. Many consumer products still include a linear power supply. This videotape will introduce you to the operation of and troubleshooting techniques for linear power supplies commonly found in consumer products. The accompanying activity booklet includes exercises which will further enhance your understanding of linear power supplies. All DC low-voltage power supplies perform the same basic functions: decrease the incoming line voltage, convert the AC line voltage to DC voltage, and maintain a relatively constant output for the needed range of load conditions. Each of these functions will be examined through circuits typically seen in consumer products. The incoming line voltage is fused and often filtered as shown here. This LC network is placed across the line to prevent RF interference on the power line from entering the product through the power supply. It also prevents noise generated in the product from being sent out over the power lines. The line voltage is then applied to the primary of the supply's power transformer. The transformer is used to reduce the line voltage to a value closer to that needed by the signal processing circuitry. Multiple secondary transformers are commonly used in consumer products to supply the variety of voltages needed. In addition to reducing the voltage, the transformer also electrically isolates the signal processing circuits from the line voltage. Some products use a transformerless supply, like the one shown here. This supply reduces the line voltage by placing a resistor in series with the signal processing circuitry. This resistor simply drops the voltage to the value needed. One obvious disadvantage of this technique is that the set is not electrically isolated from the power line. The advantages of the transformerless design are in the space, weight, and cost savings compared to using a power transformer. Transformers generally fail in one of two ways. Either a secondary will short or a secondary will open. A shorted secondary will almost always blow the fuse. If it doesn't, the transformer will become very warm and begin to smoke and smell as the insulation around the windings melts. When a secondary opens, the supply that it drives produces no voltage. One of the first tests in a defective power supply should be of the transformer's outputs. The reduced AC voltage must then be rectified into the DC voltage needed by the amplifiers, oscillators, and microprocessors found in today's consumer products. In all designs, the diode is used to convert the AC voltage into DC. Single-diode half-wave rectifiers are commonly used. A half-wave rectifier conducts to provide DC voltage for only half of the 360-degree AC cycle input. The advantage of a half-wave is low cost. Only a single diode is needed. The disadvantage of the half-wave rectifier is the extra filtering needed for high-current supplies. Two full-wave rectifier circuits are commonly encountered. The full-wave bridge uses 4 diodes to provide DC voltage throughout the entire AC cycle. The full-wave center-tapped design uses just 2 diodes and a center-tapped secondary to provide DC current for the entire AC cycle. either the bridge or the center-tapped full-wave rectifier requires more components than a half-wave design, but both require less filtering than a half-wave rectifier. The amount of current needed by the circuit being supplied generally determines whether a half or full-wave rectifier will be used. Large loads are usually powered by full-wave supplies, while light loads are powered by half-wave supplies. Diodes can fail by either becoming open or shorted. When the diode in a half-wave supply opens, the supply produces no voltage. When one diode in a full-wave supply opens, the DC output voltage will be low under load. As we have seen, the voltage produced by both half and full-wave rectifiers is, by definition, DC, but it is steadily pulsating DC, which cannot be directly used to power the signal processing circuits. The function of the filter section is to remove the pulsations from this DC voltage. Every filter utilizes at least one capacitor, which is placed in parallel across the rectifier's output, as shown here. The capacitor charges during the rectifier's conduction period, then discharges through the load during the rectifier's cutoff period, or when the DC level from the rectifier is less than the charge on the capacitor. The filter capacitor, then, provides power to the load during the cutoff period, smoothing the pulsations to produce more acceptable DC voltage. It should be apparent that a larger load current requires a larger filter capacitor. Also, since a half-wave rectifier conducts during only half the AC cycle, it requires a larger filter than a full-wave rectifier, which conducts during the entire AC cycle. It is not unusual to see more than one output derived from a single rectifier, with each output having its own filter. Many designs use two or more capacitors in parallel, rather than a single large capacitor. Filter efficiency is increased by the addition of an inductor, as shown here. The inductor stores energy in its surrounding magnetic field and feeds it to the load. Adding an inductor to a filter can reduce the size of the capacitors needed. There are, however, two disadvantages of using inductors in filters. First, inductors are generally more expensive than capacitors and add to the overall cost of the supply. Second, an inductor can be relatively large and bulky, adding to the size and weight of a supply. For these reasons, inductors are not widely used in low-voltage linear supplies. As you can see, without load, the filter produces a perfect DC voltage, with no pulsations or variations. When a load is applied, however, the filter may not be able to maintain the constant output. The resulting variation is called ripple. Ripple is generally unacceptable because it may be superimposed on the signal as noise, and because it lowers the average DC voltage output. It should be noted that if the load remains relatively constant, filter components can be selected to provide the needed DC output. Many circuits in consumer products have loads that vary. Volume, brightness, tone, function, and most other customer controls affect the load placed on the power supply. The load on this supply is an audio amplifier. Watch the effect on the supply's output voltage as the amplifier's volume is increased. Notice that the ripple grows to become almost half the peak output voltage, and that the large ripple is now discernible in the audio. Clearly, the filter needs help in maintaining a constant output voltage. The final section of a power supply, the regulator, provides a constant output voltage over a range of load conditions. A regulator follows the filter, as shown by the box here. It basically serves as a small variable resistance in series with the load. Since it acts as a resistance, the regulator has voltage dropped across it, and the output voltage is the difference between the output of the filter and the drop across the regulator. If this filter's output is 18 volts and the regulator has a 6-volt drop, the output voltage supplied to the load is 12 volts. The 6-volt drop across the regulator serves as a buffer against increases in the load. The regulator uses this voltage to maintain a constant output. It does this by automatically adjusting its resistance. As the load current increases, the average voltage produced by the filter decreases. The regulator decreases its resistance to provide a constant voltage to the load. 3 basic regulators are seen in consumer products. All rely on the natural constant voltage characteristics of the Zener diode. As you may remember, a Zener is specially constructed to be normally operated in the reverse breakdown voltage region. Here is a simple regulator consisting of a Zener connected in series with a resistor. The output of the filter is applied to the resistor, and the load is connected to the output of the regulator, which is across the Zener. Watch as the voltage applied to the regulator is increased. The output voltage measured across the Zener remains constant, but the voltage across the series resistor increases. Now watch as the applied voltage decreases. Notice that the Zener's voltage remains constant as the resistor's voltage decreases. Obviously, if the output of the filter continues to decrease below the Zener voltage, the output will decrease. But as long as the voltage is above the Zener voltage, the output will remain constant. Here, the load current demand is being increased. Notice that the output voltage remains constant, while the resistor voltage decreases. Simple Zener regulators such as this are often used in low-current circuits. They are not seen in high-current supplies because high-current Zeners, while available, are expensive. This series regulator is a variation of the basic Zener circuit and is often seen in consumer products. The Zener is again used as the constant voltage element. It is connected to provide a constant voltage on the base of the transistor. The transistor is placed in series with the load. Although the load current demand may vary, the Zener maintains a constant output voltage through the transistor's base bias. The transistor is often referred to as a series pass transistor, and its name represents the advantage of this regulator. The relatively inexpensive power transistor is in series with the load, allowing the use of a low-power, low-cost Zener. The disadvantage of this circuit is that it provides no protection against overload damage. Although thermal and shorted output protection features could be added to this circuit, it is less expensive to use a 3-terminal regulator. The 3-terminal regulator is a linear IC, which provides good regulation characteristics and output protection at a very low cost. This is a schematic of a typical 3-terminal regulator package. Because it is an IC, it is viewed as a functional component with just 3 leads: input, output, and ground. 3-terminal regulators have many advantages, and they are widely available in a variety of standard output voltages. They are available in both low-power 100 milliamp and high-power 1, 3, and 5 amp packages. They are protected against thermal and direct short overloads. If an excessive amount of current is demanded by the load, the regulator automatically shuts down by reducing its output voltage. When the load current is reduced, the regulator automatically restores its output to its rated voltage. Finally, the 3-terminal regulator provides the advantages of all ICs: less board space and lower cost. Here is a typical 3-terminal supply. Notice that a simple capacitor filter is used, and that a small filter is placed across the output to help the regulator. It is not unusual to see a small capacitor in the range of 0.01 to 0.1 microfarads placed across the output of the regulator. This capacitor dampens high-frequency ringing that can cause the regulator to oscillate at 10 kilohertz or higher. Because its circuits need a variety of voltages and currents, a typical power supply in a television, VCR, or other consumer product may include all of the rectifier, filter, and regulator circuits discussed. A low-current circuit may be powered by a half-wave rectifier with a single capacitor filter and a simple Zener regulator. A higher current circuit may include a multiple capacitor filter and a high current regulator implemented with a series pass transistor circuit. The digital circuits are often powered by 3-terminal regulator supplies. Each supply is carefully designed for economy and efficiency. The techniques used in troubleshooting a linear power supply are relatively straightforward. The multimeter and oscilloscope are the only test instruments needed to identify most problems. All safety procedures should be followed when troubleshooting a power supply. Remember that it is line-powered and potentially lethal. When servicing a transformerless supply, always use an isolation transformer. When diagnosing a power supply problem, you should always remember that a power supply failure can be produced by either a component within the supply or by the signal processing circuit connected to the supply. When the problem in the supply has been corrected, the technician should carefully consider the source of the problem. Oftentimes, a supply must be repaired twice. The first repair fixes damage to the supply, but a second repair is needed because the technician didn't find the original cause of the problem. Two failure modes are most often encountered in linear supplies: no voltage and low voltage. The no voltage condition is often accompanied by a blown fuse. Whenever a no voltage symptom is encountered, the fuse and line filter should be checked first. If the fuse is blown, the transformer is not receiving power. Blown fuses are common, while failures in the line filter and primary circuit are not. Measuring the voltage into the primary is a simple test, however, and should be performed. When the fuse is blown, a careful visual inspection of the power supply components may reveal the source of the problem. Heat-darkened diodes, capacitors, and regulator components should be suspect. If a visual inspection does not indicate the source of the problem, replace the fuse and measure the resistance of the supply across its output. If the resistance is very low, disconnect the load. If the resistance increases substantially, then the problem is most likely in the load circuit. Apply power to the unloaded supply to verify the diagnosis. If the fuse immediately blows, there is a shorted component in the supply. Using the multimeter, perform resistance checks on the rectifier diodes. Notice the effect of a shorted diode in this full-wave rectifier. During 1/2 of the AC cycle, one end of the secondary is shorted to the other through the defective diode. If the diodes are okay, perform resistance tests on the filter capacitors. A shorted capacitor places a direct short across the transformer. Finally, check for shorts in the regulator components. A shorted Zener or pass transistor will often cause an overload condition. Observe the regulator components carefully for signs of excessive heat. When the defective component has been identified and replaced, perform continuity tests on the other supply components. It is not unusual for a shorted Zener to also cause the pass transistor to fail. If the transistor is not replaced, it will in turn cause the Zener to fail. Don't assume that just a single component is at fault. If a supply's fuse is blown, but the supply seems to function without load, 3 possible problems exist. A power supply component may test fine without load, but fail under load. The most likely candidates here are the regulator components. The Zener and transistor should be checked with in-circuit device testers. The second possibility is a failure in one of the load circuits. Often the defective circuit can be identified by reconnecting only one circuit at a time to the supply. When the defective circuit has been identified, close inspection of the components may help identify the problem. If the power supply is on the same circuit board as the load circuits, observation of the individual supply outputs with a voltmeter may help identify the defective load circuit. Warm components may also indicate which area of the board is causing the problem. Never short the fuse and apply power to the supply, hoping to identify the defective component. This technique generally produces more bad components than it identifies. If these techniques do not point to the source of the problem, connect the supply's line input to a variac. Adjust the variac to produce about 30 volts and observe the system. If the fuse does not blow, measure each power supply output and check the load circuits for the first signs of improper operation or overheating. Gradually increase the variac's output. Generally, the load circuit which is at fault will begin to overheat and fail before the fuse blows. After the problem in the load circuit has been repaired, it is good practice to repeat the variac test to make sure that other components are not also defective. Often, the no output condition is not accompanied by a blown fuse. Voltage checks indicate AC voltage to and from the transformer and DC voltage at the filter. If voltage is present at the input to the regulator, but no voltage is present at its output, the regulator may be defective. The second initial symptom of a power supply failure is low voltage. This symptom is often observed in abnormal operation of the product. Video or audio noise, change in video size or shape, irregular or improper operation of the control section of the product may all result from low voltage output. Low voltage problems are often produced by a diode failure. Watch the output of this full-wave rectifier decrease when one of the 4 diodes is open. When a rectifier diode fails, it shows up only under load, so be sure to check the supply under load. An open diode is easily identified by a multimeter continuity test. Low voltage will also be produced if the filter capacitor opens. A quick resistance test should identify an open filter. When either a diode or a filter capacitor opens, excessive ripple may result. A multimeter will generally average the voltage applied to it and not indicate the existence of excessive ripple. When troubleshooting low voltage problems, observation of the filter's output on an oscilloscope can often help pinpoint the problem. Low voltage problems in the regulator section should not be overlooked. If the zener or its resistor opens, the voltage produced can be higher or lower than the desired output. If a 3-terminal regulator opens, a low voltage condition can occur. Testing a 3-terminal regulator is as simple as checking for proper input and output voltages. If the regulator's output is low and the regulator is hot, a short in a load circuit is indicated. If the output voltage is low and the regulator is cool, a defective regulator is indicated. Generally, when an IC regulator shuts down, it reduces its voltage to 1 volt or less. Care should be taken when replacing 3-terminal regulators. Although they are quite hardy when installed properly, they will often be destroyed if installed backwards. Low voltage symptoms can also be produced by a failure in the signal processing circuit being powered. Observing the suspect load circuit for symptoms that point to the problem can often identify the trouble. The traditional linear power supply has been the workhorse of the consumer products industry and is likely to remain so for many years. Familiarity with its design and good troubleshooting techniques can make it easy to maintain. To learn more about linear supplies through hands-on activities, see the accompanying activity manual. For more information about the operation and servicing of switching power supplies, obtain a copy of the Consumer Electronics Group's Switching Power Supply videotape. Write, the Director of Product Services, Consumer Electronics Group, Electronic Industries Association, 2001 I Street, Northwest, Washington, D.C., 20006.